Radu Ignat and Giacomo Canevari couldn't join us, unfortunately, today. So yeah, it's a pleasure to announce the talk of Radu, who will be telling us about the minimality of the vortex solution for the Ginzburg-Landau systems.
Thank you very much, Argir. Hi to everybody. Many thanks to the organizers for the invitation. I regret that I cannot be with you these days. In 2019, during our semester, I spent a very nice time at Newton Institute, and I really hope that in the next future we will have the opportunity to meet again. So my talk is about the Ginzburg-Landau model, more precisely about the minimality of the vortex solution in ball domains in any dimension. So this talk is part of a series of works jointly with Luc Nguyen, Michael Naon, Mircea Rus, Valery Slastikov, and Arghir Zărnescu. So the Ginzburg-Landau model was already mentioned several times during these days, in particular in the talk of Luc on Monday. So the context here is that I will always work on the unit ball in any dimension n larger than 2. The order parameter will be always an n-dimensional vector field that is defined in the ball, in the unit ball, with n components. And I will consider the following Ginzburg-Landau functional that has a kinetic part, this Dirichlet energy, and then this potential energy that depends only on the distance of u to the unit sphere. So this distance is given, is modeled by a scalar function w that is, like in this picture, is a convex function. It's a convex function that has a unique 0 in 0 and is strictly positive away from that. Okay, so if you want, just think that w is t squared all over this talk. Okay, so if you minimize only this potential energy, then the minimum will be when u is a unit length vector field. So in front of this potential energy, you have a parameter epsilon that here it will be fixed. Of course, can be small, can be large. So maybe what is very common to study is when epsilon goes to 0. So if epsilon goes to 0, this part is huge. So for example, if you want that the energy is uniformly bounded, then you will have to be close to the minimum point. So the modulus should be close to 1. So like this, you get to the harmonic map for sphere-valued for sphere-valued maps. So that's why the results that we aim to get are motivated by the results that one can get for the harmonic map problem. So the focus of this talk will be on critical points, on this energy. So the critical points is given, so it's a system of n elliptic PDEs given here under the Dirichlet boundary condition that is the suitable one when you speak about the degree 1 vortex solution, that is identity on the boundary. Okay, so this is how you get, for example, the degree 1 of these vector fields. So when you have a system of PDEs like this, mainly there are three questions: existence, uniqueness, regularity. So existence is easy you just use the direct method, you take a minimizing sequence, you prove that it converges, and you get the minimizer, and then you get the critical point. Of course, another way to prove the existence is, for example, to prove that the vortex solution exists for every epsilon, so that's a solution, it's a critical point. Regularity is also easy, so every critical point will be C infinity up to the boundary. And how you get it? Well, first, there is a maximum principle for the modulus of a solution. In fact, you can prove that, that the modulus of U stays always less than 1 inside. So like this, you get that this right-hand side is L infinity, and then you run the standard elliptic regularity to get that U is C infinity up to the boundary. So the third question is the uniqueness, and that's the main goal of this talk, is to prove that, yes, the conjecture is that for every epsilon, there is a unique solution, which is the vortex solution. So what is this vortex solution of degree 1? Well, that's the unique solution that is invariant by the symmetry group that keeps invariant the energy and the boundary condition. So in fact, there is this group action generated by the rotations. So how it goes, you make a rotation in the definition domain, and then you rotate back in the target. Okay, so this, as I said, keeps invariant the energy and the boundary condition. And then you can prove that within this constraint, there is a unique solution of the PD that is given by the so-called vortex solution that has this form. So the director is this x over modulus of x, which is this harmonic map of unit lengths that has a singularity in 0. Okay, and in front of this you have a radial profile f epsilon that is 0 in 0. So like this, it cancels the singularity, because we know that every solution, as I said, should be C infinity. Okay. So what is important to keep in mind is that the vortex solution, we always have a 0 at the origin. Okay, so this radial profile is very well studied. So it's the unique solution of this second order ODE. So is 0 in 0, 1 in 1, yeah, to match the boundary condition, and is increasing. And this scale epsilon is after which f epsilon will be very close to 1. Okay, so that's the length scale of this model. So, for example, you can also prove that this is it behaves linearly in 0. Okay, so the properties of such solutions were very well studied. Here are some references, and you should keep in mind that it stays between 0 and 1 and is increasing. Okay, so as I said, the main point is to prove that for every epsilon, this is the unique solution of the PD system, provided that you impose this identity at the boundary. Okay, in fact, I will address an easier problem, which is the minimality of this vortex solution. So the question will be that, is this vortex solution a minimizer under the boundary condition for every epsilon? And if yes, is this the unique minimizer? And then, of course, the next step will be, is this the unique critical point? So there is an easy case when epsilon is large. So what's happened when epsilon is large is that when epsilon is large, so this is small. So if you want, you can see this as a perturbation of this strictly convex function. So using the convexity of this W, you can prove that after a certain epsilon, also this functional is strictly convex. So So as we know that there is always a minimizer, right? As I said, so then you get uniqueness, existence and uniqueness in the PD. And since the minimizer exists, so you get also the minimality of this vortex solution that will be the unique solution. Okay. So the delicate problem is what's happening below that epsilon when this energy is strictly convex. So 30 years ago, there were a lot of works in the dimension 2. So the first partial result was due to the, in the seminal work of Betuel, Brésis, Hélin, where they proved that the zero of a minimizer of our problem will converge to the origin. And this was thanks to their theory of renormalized energy between the vortices. Okay, after that, it was Paccard and Rivière that proved that, in fact, the vortex solution is the unique critical point for very small epsilon. Okay, there is not a precise epsilon because it's like a contraction mapping theorem. So anyway, there is still a gap remaining given in dimension 2. But their analysis is a very delicate one. In fact, they wrote a book, and around page 200, you have this this theorem. Okay. However, if you blow up the ball into the plane, the problem is much easier. So Mironescu proved it in one page using the Pozaev identity. So why in R2 the things are much easier than in a ball? Because, so of course you have to impose a suitable condition at infinity, but in particular at degree 1. So imposing this, you know that every map will have a 0, and then what you do is that you fix the origin of your coordinates in that vortex point, and then you can run. For example, you can use the ground state decomposition that I speak in a moment, and use the Pozaev identity. But of course, this you cannot do it in a ball because, right, the 0 cannot be in, maybe it's not in the origin, and then okay. You cannot do directly this method. And in fact, the main goal in Paccard-Rivière book is to prove that the 0 is in 0. And once you know this, for example, you can run also the method of Mironescu. So in dimension 2, of course, there were several other works. I don't want to quote everybody here because anyway, I will miss persons. And in dimension higher than 3, the only results were in the full space, Rn instead of the ball. And so in some sense, the generalization of the results of Petru Mironescu by Vincent Millot and Adriano Pisante, and then by Adriano in dimension higher than 4. So as I said, the problem is still open for in the full range of epsilon in any dimension. Oh, okay. Before we started work. Okay, so let's go back a bit to the ball when the domain is the ball. And of course, if we want to prove that the minimizer is unique, better to prove it that this is true for in the limit when epsilon goes to 0. So for the harmonic map problem. So this is a question that was positively answered first by Jäger and Kaul in large dimensions, and then Brésis, Coron, and Libby in dimension 3, and then Lin proved it in any dimension higher than 3. So here I missed the dimension 2 because in dimension 2, right, the Dirichlet energy is infinity. So right, you cannot speak about minimizing. Okay, so now let's go back to the Ginzburg-Landau. By the way, if you have questions, please interrupt me. Okay, otherwise I will start with our first result that is in dimension higher than 7, which in some sense is similar to the result of Jäger and Kaul for the harmonic map problem. And this we obtained in 2018 with Luc, Valérie, and Argir. So in dimension higher than 7, the vortex solution is the unique minimizer under the identity boundary condition for every epsilon. Okay, and as you will see, again, so it's the proof, it's easy, it's 2 pages. So how it goes? So you want to prove that this is the minimal energy. So when you perturb the vortex solution, you expect that this excess of energy is positive, right? So that's, yeah, from after each perturbation that is 0 at the boundary. Okay, so we do this in 2 steps. So first, we will get a lower bound that comes like a kind of linearization of the potential energy. So here we will strongly use the convexity of the potential W. So in some sense, what you use here is that the potential energy is higher than the tangent in 1 minus u epsilon squared, so which is like the potential energy for the vortex, okay? So like this, if you just replace W by this linear function, then this becomes quadratic. You use that u epsilon is a solution, and you get, it's an easy computation, you get this quadratic form, okay? Quadratic form in this perturbation map. So careful here, this is not the second variation. This is not the second variation of the Ginzburg-Landau energy in u epsilon. Okay, so the aim will be to prove that this is positive. Okay, so how you prove it? So of course you can do it component by component, and since it's a quadratic energy, the only thing that you need to prove is that the first eigenvalue of this linear operator is positive, right? Once you prove it, you get that the u epsilon is the minimizer. Okay, so then we started to study the first eigenvalue of this operator in the unit ball with the 0 Dirichlet condition. Okay, let's call it L epsilon. And we prove that this first eigenvalue is larger than a constant that is given here, and which in dimension higher than 7, when you do the numerology, is strictly larger than 0 for every epsilon, so then you won. Okay, so how do we prove it? So here we use, as I said, this kind of ground state decomposition. We called it Hardy decomposition. Each domain, each name in probability is called dupe transform. So how you do it? So first of all, you will restrict to, you can restrict yourself to C infinity functions that are compactly supported around 0, because a point has 0 capacity, H1 capacity. And what you do is that you decompose V with respect to the radial profile of the vortex. Okay, and then you get this C infinity quotient S. And then you use what is called, sometimes called Poisson identity, that your quadratic functional decomposes in 2 terms. So this term, what happens is that the quotient S is like going out here, right? So it's, and then it remains, it will kick, this operator kicks only the radial profile, so this ground state at the radial level. Okay, and then you have a second term that is this gradient of the quotient S times the radial profile. Okay, and then you use the ODE for the radial profile, and you get that this is a negative term, and then you get this. So this is always identity, right? So integration by parts is not very difficult. And then you ask yourself, okay, is this positive? So okay, if you forgot, if you forget this thing, then it's like, how can you bound, lower bound the H1 norm with this L2 norm of S squared over R squared? So then the Hardy inequality rings the bell. Okay. So how do you prove it, right? We want to prove that it's positive for every epsilon. So let's look what's happening when epsilon goes to 0. So this really goes to 1. Okay, so then you forget this. So this quadratic functional converges exactly to this term. And then you use Hardy inequality, so better to know what's the best constant, this n squared minus 2 squared over 4, right, that you see it here, minus n minus 1, right? So, so as I said, in dimension 7, this is positive, so, okay, r is less than 1, so then you get that this is larger than, okay, it's s squared, so this will be less or equal than the first eigenvalue. Okay, so in the limit, it's good. It's a good hint that it will work. So what you do at the fixed epsilon, well, then you just remember how you proved the Hardy inequality. So again, you will use this kind of ground state decomposition with respect to this power function, right? And then when you do the things here, so of course when you do integration by parts, you have some derivatives here, but the only thing you need to know is that f epsilon is increasing as stays between 0 and 1, and then you prove the same inequality as here. Okay, so in particular this is positive and you won, right? You know that your vortex is minimizer. And more than that, you get also uniqueness because, right, if you take another minimizer, then the excess should be 0. So this quantity should be 0. So that perturbation V, right, that perturbation V should be 0, right? So then you get uniqueness of your minimizer. Okay, but you see that you need that this is positive, right, in order to fulfill the proof. So, and that works in higher dimensions. So then, of course, the question is, what's happening in dimension between 2 and 6? And this we worked with Luke 4 years ago. And the situation is the following. So, in fact, everything is given in this picture. So in dimension 2, between 2 and 6, there will be a critical epsilon below which the first eigenvalue of that linear operator is negative. So you cannot hope that this method will work anymore. However, as we proved, is that if epsilon is larger than epsilon n, then the vortex solution will be the unique minimizer. And what is nice is that you can prove that this epsilon n, so write this critical epsilon when after which the first eigenvalue is positive, is strictly less than the epsilon after which the energy was convex, right? So in some sense, we improve the gap even in dimension 2 for the uniqueness of the minimizer in the general Ginzburg-Landau system with respect to this boundary condition. Okay, so again, the minimality is still open in every range below this epsilon n. Okay, and then what we do with Luke, we said, okay, maybe it's too ambitious to prove directly the global minimality. Let's prove the local minimality. And so this question was already known to be true in dimension 2 by Mironescu and Liebenloos. Okay, and then we proved it that also in dimension 3 to 6, this is true for every epsilon. So how it goes? So again, right, you want to prove that at least in a small neighborhood of the vortex, this excess of energy is positive. And in fact, we prove this coercivity in a small H1 neighborhood of the vortex. So mainly this is proving that the vortex is stable, so in dimension 3 to 6. So you look to the second variation, and so like this, it's a good way to see the difference between the quadratic energy that I used. So you know, as we know, right, when epsilon is small, this can be negative, right? When epsilon is small. But the hope is that the remaining thing in the second variation, right? So here you see that the convexity helps because this is positive. We have to get that this is positive, and in fact, this is how you prove, yeah, that the second variation is it's a positive definite form. So here we use some careful Hodge decomposition in the tangent space, and then spherical harmonic decomposition for the coefficients, scalar coefficients. Okay, and then we get the stability, and then you have to work a bit more to get the local minimality. Okay, so is this story end is finished in dimension 2 to 6? Well, no. So we really wanted to see, okay, what's the end of this method, this easy method? And in fact, we looked what is called the Ginzburg-Landau model for gradient fields, so-called Aviles Giga model. So Aviles and Giga, in fact, they used it to model smectic liquid crystals. So it has a meaning to restrict yourself to gradient fields, because the vortex is nothing but the gradient field coming from the radial profile. Okay. So the question is the vortex solution the unique minimizer when we restrict to this class of gradient fields? So the gradients are identity at the boundary, right? So in particular, all the tangent derivatives are zero, so you can always assume that phi is zero at the boundary. Okay, and then of course you should look to this like fourth order operator, so not the second order operator. But the easy thing is that phi now is a scalar. Okay? So of course, right, we know that this question is true in dimension higher than 7. You just right, you know that it's true in this higher generality. So the question is how it goes in dimension 2 to 6. So in this case, we together with Michael now and Luc, we prove that this is still true in dimension 4, 5, and 6. Okay, so the vortex is the unique global minimizer for every epsilon in this class. So let me sketch you two proofs. So the first proof is related, is the same idea with this kind of linearization of the potential energy. So as before, right, we know that the excess is larger than that quadratic energy. But now, since this psi is 0 at the boundary, the Hessian is nothing but the Laplacian squared. Okay, and you want to prove that this is positive when you restrict to these gradient fields. So again, what you do is that, okay, let's see what's happening in the limit when epsilon goes to 0, and then try to come back and prove it for every epsilon positive. So when epsilon goes to 0, so this is like the right-hand side in the Ginzburg-Landau part, and then, of course, you know that this always goes to the Lagrange multiplier for the harmonic map problem, and then you get this thing, right? So this was what we looked before. And now the hope is that this restriction to gradient fields, maybe it will get you in the this Hardy-Rayleigh inequality, a constant that will beat this n-1. Okay, and then you look to the literature, and of course these questions were known. So in dimension, so what's the best constant in this Hardy-Rayleigh inequality? So by 30 cas in dimension higher than 5. So what is nice here? So first you look, you said, wow, what's happening? Is that, so you remember that the constant before was n-2 squared over 4. So now when you restrict yourself to gradient fields, what's happening, it's like your dimension shifted by 2 below, right? So the constant will be n squared over 4 instead of n minus 2 squared over 4. Okay, so that's right. You know that in dimension 7 it worked. So it beats this n minus 1. And then in dimension 3 and 4, the question is much difficult because the optimal function here is not radial anymore. You have to go into the first spherical harmonics. And these constants were proved by Beckner. So it's n minus 1, which is good, right? It's exactly what you need here to, yeah? But in dimension 3, it doesn't work, okay? Okay, so in dimension 4 to 6, this argument gives you a good hint that it will work, and then you go back to epsilon strictly positive, and you do a delicate analysis using spherical harmonics, and okay, finally you can prove it that this is still positive, and then this is the unique minimizer. Okay, and now the second proof that in fact it will work only in dimension higher than 5. It's with respect to the symmetrization of vector fields. So, of course, if you think to scalar functions, there are a lot of symmetrization techniques. Maybe the most common is the Schwarz decreasing rearrangement. So how it goes for the scalar functions, well, you will rearrange the level sets, you will make it radial, and then you will decreasingly rearrange them. Okay, so like this, the level sets have the same area, so the LP norm is the same, and then you can prove that the H1 norm decreases. Well, at my knowledge, this is an open question how to symmetrize vector fields in order to have such kind of properties. But in fact, for the gradient fields, we succeeded to do the following symmetrization that will satisfy what we want in dimension higher than 5. So how it goes? Well, you will look to the gradient of a stream function phi, for which you will associate another radial stream function that is given by what? So what you want to do is that you want to conserve the L2 norm of the gradient on each interior sphere centered in 0. So mainly, if you want, this is like a rearrangement in the Fourier modes, okay? And so this, in some sense, rings the bell with the method of Lenzmann that was so his method of symmetrizing scalar maps was to look to the Fourier transform, symmetrize the Fourier transform, Fourier inverse back, okay? So this is a bit similar, but do it not in the full space, but on spheres. Okay, so clearly the L2 norm of the gradients is conserved. And since W is convex, then you just use Jensen, and you prove that always your potential energy will be decreased by this symmetrization method. So then the only question is the H1 norm of the gradient decreased by this symmetrization method? And this is true if the dimension is higher than 5. Okay? And in some sense, this is related with the previous inequality that I mentioned here, is that in dimension 3 and 4, when you look, for example, to these inequalities, the radial function is not anymore optimal. Okay? So in fact, for example, you can prove that this inequality is still true if you are orthogonal, if you are orthogonal to the first spherical harmonics. Okay, and once you prove this, so in dimension higher than 5, then you get to radial functions, and then this is easy, right? You know that the vortex is is in some sense the unique. You know that in this equivariant class, it's the unique solution, and you're done. Okay, so finally, let me give you another setting where, in fact, you can solve the problem completely in dimension 2 and 6. So up to now, I always spoke about n-dimensional vector fields. So what I will do now is that we will add an additional component in the target. Okay, so
5 minutes, yeah.
Yeah, thank you. Yes, this is my last slide, in fact. Okay, so we look to these n+1 vector fields defined in the ball, the same energy, and the boundary condition is that you restrict yourself to the sphere in the hyperplane, in the horizontal hyperplane in dimension Rn+1. Okay. So of course, the argument that it worked in our first paper with Luc Arguil and Valerie will still work also in this setting. And so in dimension higher than 7, you know that the vortex. So what's the vortex solution? Is the vortex that stays always 0. So it's like confined in this hyperplane. Is the unique minimizer. So the question is, what's happening in dimension 2 and 6 always? That's the trick. So with Mircea-Rus, we proved that in this context, every minimizer is radially symmetric. I mean, you should have a kind of a vortex solutions, and you have the following dichotomy in dimension 2 and 6. And here you will see why that epsilon n, you know, that critical epsilon below which that first eigenvalue became negative, will play a crucial role. So in fact, this is the picture that you should keep in mind, right? So that epsilon n played the role that if I here, the first eigenvalue of that linear operator was negative. Okay, so what you can prove is that epsilon is, if it's larger than epsilon n, again, the previous argument will work again, and you know that this vortex solution, that so-called non-escaping vortex solution, is the unique minimizer. Okay? So what's happening when in the nice region when epsilon is strictly less than epsilon n, when here you will have two escaping vortex solutions. So what will happen when epsilon is less than epsilon n is that the system will prefer not to stay confined, so to escape in this additional dimension. So this is was already known for example, when you look to harmonic map problem for the equator map. Okay, and you get exactly two escaping vortex solutions that will be the only two minimizers of this energy, and in this region, this non-escaping vortex solution will lose the stability. Okay, so right. So the problem is solved, right? So you know what's happening at the minimizing level, right? So careful. This is not this is not the same radial profile as here. So in fact, the picture is similar to the radial profile that I described, but then you need to have also this escaping radial profile, and of course always you have that the modulus is less than 1. Okay, so thank you very much.
Questions, comments? Then I have a question, Radu. So
Yes.
some of these results are strongly dependent on the potential being W of U 1 minus U squared, right? W can be quite general, but you always have this 1 minus U squared. So what if you take a potential which is something like W of modulus of U? yeah, something like as you have in Q-tensor theory, fourth
Yes.
order polynomial,
Yeah.
but now in
Yeah.
Q in modulus of
Right.
Q.
Right. Well,
How much
so of
do you
course.
see could survive out of these?
Right. So we know, right? I mean, in what we studied. So right when we studied the hedgehog, right? So the equivalent of the vortex solution will be like the hedgehog solution, right? So the only thing that we succeeded to prove in that regime, right, when is that the hedgehog is stable, right? Because in the opposite regime is not stable. So right is there where, right, the question would be that that hedgehog should be also global minimizer, right? But okay, we tried hard, and yeah, so definitely in the method we succeeded to prove, yeah, the global convexity plays an important role. So of course, right, also in the works we do now, right, the same team. So if you impose
you
only
have some sort of local convexity near the
zero,
middle,
right? So then, of course, if you have only this, then maybe that some hope it will be that that's true when epsilon is small, because in some sense you are confined there. I mean, yeah, I mean the most part of your map. But of course, then I believe that you can cook up critical points that are not don't stay equivariant if epsilon is like in the middle, right? Because always, right, when epsilon is small, is large, you also have convexity. So there's always a gap where but okay, in this Ginzburg-Landau, the thing is, the conjecture is that the vortex is the unique critical point.
Okay. Yes.
So, Radu, thanks, Radu. So in the Parker-Rivier's work, right? So the beginning, instead of solving that uniqueness, they show uniqueness when you prescribe the location of the zero.
Exactly.
Is there some analog of that for high dimension?
I'm not aware of that. I don't think so, because it's well, right. So of course, in order to do that, you will use a lot these Jacobi fields, and in some sense, you will use mimic also the positive identity, but with respect to different, not right dilation, right, with these different fields. So in the when you blow up the ball, right, there are all these results of Mio, Pisante, and Pisante. So of course, now the question is, can you have this kind of calibrations when epsilon is small? But I'm not aware at all that in dimension 3, for example, if you have this.
Okay, any other question? No. Let's thank Radu.
Thank you very much.